GCE Advanced Level Chemistry Practical Series, Experiment number 4, Preparation of Standard Solutions. In this practical, we are going to learn how to use or how to handle glassware, how to use a triple beam balance, and we are going to teach you how to measure volumes as well as how to prepare a solution of a particular concentration. Now let's move on to the reagents and the equipment we will be using for this practical. In this practical, we will be using sodium carbonate. What we have here is sodium carbonate 10H2O. We'll be using this to prepare our standard solution. And to weigh the right amount of sodium carbonate, we will be using a triple beam balance. We can also use a digital balance like this one, so we will be using that as well. And we will be using a 250 milliliter volumetric flask, a funnel, a watch glass, and a wash bottle containing some distilled water. Now, let's move on to our experiment. In this practical, we will be using our triple beam balance for the first time. So, let's learn how to use it. Before we use it, we have to identify the parts that is present in this triple beam balance. We have our base here, so everything that you see on this triple beam balance is present connected to our base. And here we have our stainless steel weighing pan. So we will be placing whatever the objects that we need to weigh on top of this weighing pan. And you can see over here there are 3 notched beams. The first notch we see here goes from 0 grams to 100 grams with 10 gram graduations. And we have our second beam. It goes from 0 grams to 500 grams with 100 gram graduations. And then finally, we have the last beam over here that goes from 0 gram to 10 grams with 1/10 of a gram graduation. When using the triple beam balance, we have to make sure the line you see over here, you can see a straight line over here, and on this part of the triple beam balance, you see a line with a 0 written next to it. So these 2 lines indicate us whether the triple beam is balanced or not. When measuring a mass using the triple beam balance, we have to make sure the 2 lines you see over here, the 2 lines you see over here should balance. The line that you see on the beam of the triple beam balance should align perfectly with the 0 line over here. When it aligns like that, it indicates that the triple beam is now at a balance. So, whenever you place something such as this watch glass on the triple beam balance, we can see the 2 lines now no longer align. This indicates that this side of the balance is heavier. So, to balance it, we will be moving these metal pieces that is connected to the triple beam, which are known as riders, or sometimes we call them sliders as well. So, when you keep on moving them, at one point, we get to the point where the 2 lines will balance once again or align once again. So, at that point, we can say we have accurately measured the mass of this watch glass. Now, let's start measuring the mass of this watch glass accurately. So, in order to do that, I will have to turn this towards myself. Before we start this experiment, we have to make sure the two lines align perfectly. If they do not align perfectly, there is an adjustment knob over here. We can use this adjustment knob to make sure the two lines align perfectly before we start our experiment. When we have noticed that the two lines present on the arm of the triple beam balance and the base of the triple beam balance are now aligned, we can move on to weighing the mass of this watch glass. So, in order to observe if the two lines perfectly align, you have to bend down and take your eye level to the level of the two lines and observe if the two lines are perfectly aligning. You should not observe it while standing up like this, because you will not be able to get a clear enough view of the two lines standing upright like this. After observing that the two lines are perfectly aligning, we can place our watch glass on the triple beam balance. As you place the watch glass, you can see the arm has now moved up. This is no longer aligning with the zero line present on the base of this triple beam balance. So now, to make it come to that alignment again, we can start moving these riders. We first start with the middle beam, where it has 100-gram graduations. So we will move this rider in the middle beam. When I moved the 100-gram rider, you can see now the beam is at a position that is way below the 0 point, meaning that this watch glass is definitely lighter than 100 grams. So we move it back, and then we start moving the 10-gram rider. So we move it to the 10-gram position. We do not see a movement here, so we move on to the 20-gram position. Again, still no movement. We can move it to the 30-gram position. We do not see a movement, so we move it to the 40-gram position. As you can see, when we moved it to 40 grams, the triple beam balance is no longer in balance again, but this time around it indicates the right hand side of the balance is heavier than the left hand side, telling us this watch glass is not as heavy as 40 grams. So we move it one notch backwards. As you can see, there are notches on the triple beam balance. Now it is at 30, and now we finally move on to the last beam of the triple beam balance, where there is 1/10 of a gram graduations. So this last beam, we can very carefully move the rider to see at which point this beam will come down from this position and balance with the 0 line. We can do it slowly. Now we can see the beam is starting to move downwards, but still did not align with the zero. That means we have to move the rider further to the right hand side. As you can see, when we are trying to balance this mass over here and get the reading, the pointer of the triple beam balance starts to oscillate up and down. And when we have accurately measured the mass of this, these oscillations will happen in such a way that the center point of these oscillations balance or align perfectly with the zero line of this triple beam balance, indicating that we have accurately measured the mass of this watch glass. So right now, we can see the oscillations have come to a stop, and at the same time, the pointer of the triple beam balance aligns perfectly with the zero line of the triple beam balance. So now we can move on to measuring the right amount of sodium carbonate using this reading. Before that, let's take a look at what the reading here is. So our first beam reading is at 30, indicates we have taken 30 grams there, and the second beam is at 0, and the third beam is at 8.7. It is at 8.7 exactly. So this reading is 38.7. So we have this watch glass that has a mass of 38.7. Now, this triple beam balance has given us a reading because the pointer aligns with the zero line, and that reading is 38.7. We have our first beam rider on the 30th gram position, and the last beam rider on the 8.7 position, and the second beam rider was not moved because this was not heavier than 100 grams. So the final reading as it stands is 38.7 grams. Now, let's take a digital balance. What we have here is a digital balance. We can use digital balance as well when it comes to measuring masses within a lab environment. So now let's take our watch glass and place it on our digital balance and observe if we get the same reading. First of all, our digital balance reads 0 and the measurement unit is grams. Always check that, because sometimes certain digital balances give you measurements with different units. So then you have to adjust the digital balance in order to get to the unit that you want. So we have grams here and it reads 0.00. Now let's take our watch glass and place it on our digital balance. Now, when we placed the watch glass on our digital balance, we saw the reading we obtained was 38.70. The same reading we obtained using our triple beam balance. This tells us the reading that we obtained was accurate because we used two methods for measuring the mass of this watch glass, and both the methods gave us the same reading. Now, let's move on to measuring the right amount of sodium carbonate. Now, we are about to prepare a standard solution, and we are going to measure the sodium carbonate. We need to prepare the standard solution. So, what is a standard solution? A standard solution is a solution where we know the concentration quite accurately. When it comes to preparing a standard solution, you will be using a primary standard. So there are few qualities of a primary standard or solid that is used as a primary standard. Usually students, a primary standard should have a high purity. It should be quite stable. Apart from that, a primary standard should be anhydrous. It should be not hygroscopic, meaning it should not be absorbing water from the surrounding. So if the solid absorbs water from the air, or if it absorbs moisture from air, it is not going to be suitable as a primary standard. Apart from that, it should have a high molar mass. It should be non-toxic. It should be easy to weigh. It should be commonly available and inexpensive as well. So these are the properties that should be found in primary standards. To summarize, primary standards should have a high purity. They should be stable. They should not be hydrated compounds, so they should be anhydrous. They should not be hygroscopic. They should have a high molecular mass. They should be easy to weigh. They should not be toxic. Apart from that, they should be quite inexpensive and commonly available, so that we can carry out this type of reactions easily. So students, these are the common properties that you see in primary standards. Now, after going through the list of properties that a primary standard should have, when we observe the sodium carbonate that we have here in the lab today, you would notice something. The sodium carbonate we have in the lab today here is not a primary standard. Why is it not a primary standard? Because it has 10 water molecules in each sodium carbonate, meaning that this is a hydrated compound. Sodium carbonate 10H2O. This is not an anhydrous compound. Primary standards should not have any water bound to them, because at that point you can't be very sure about the mass of sodium carbonate present in a sample of sodium carbonate 10H2O. Certain sodium carbonate might have 10H2O with them. Some might have a lower number of water molecules attached to its sodium carbonate. This might introduce some errors when it comes to calculating the exact number of moles of sodium carbonate present in a sample that we have measured. So therefore, students, it is always preferred to obtain an anhydrous sodium carbonate sample when you're trying to produce a primary standard solution using sodium carbonate. You can prepare an anhydrous sodium carbonate sample using this sodium carbonate 10H2O we have here. We will take a small mass of sodium carbonate 10H2O and we will transfer it onto our crucible here. Like I mentioned earlier, we will heat it then to a temperature of 373 degrees Kelvin and above. So you have to heat it to a higher temperature, and then if you heat it for about 45 minutes, all of the water will be removed from the sample. In other words, you can heat the sample to a higher temperature than 100 degrees Celsius until a constant mass is obtained. So if you heat it for about 45 minutes, we can actually be sure that all of the water is removed from the system. But if you don't want to wait that long, you can actually heat it to a temperature greater than 100 degrees Celsius, and you can constantly measure the weight of this sample, and by the time that you obtain a constant mass, you can be sure that all of the water is removed from the system. So now we are going to be doing that. So we have our sodium carbonate that we have in this bottle here, sodium carbonate 10H2O, and we will be transferring a small amount of sodium carbonate onto our crucible here. Now what we transferred was sodium carbonate 10H2O, and now we will be heating this sodium carbonate until all of the water in the sodium carbonate 10H2O is removed. Now we are going to use a Bunsen burner to heat this sodium carbonate sample. So we use a crucible here because we are going to subject this sample into somewhat of a higher temperature, a temperature greater than 100 degrees Celsius or temperature greater than 373 degrees Kelvin. So therefore, we will be using a crucible here, and we will heat this up until all of the water is removed. So we will be heating this up for about 45 minutes, and I will meet you again after we have heated the sample for long enough to remove all of the water from the sample. Now students, we have heated the sodium carbonate 10H2O sample that we took into our crucible for about 45 minutes, and we have allowed it to cool down as well. Now it is cool to the touch, you can touch it because it has cooled down to room temperature. So we have now prepared our sodium carbonate sample. It is no longer having any water in it. So this is our sodium carbonate anhydrous sample. Sodium carbonate anhydrous sample. I will take a small amount into the petri dish, leave the rest in the crucible itself. So we have now prepared our primary standard, which is sodium carbonate without any water in the sample, or in other words, anhydrous sodium carbonate. So students, we are going to prepare 250 milliliters of sodium carbonate solution, and the concentration of the solution should be 0.1 moles per decimeters cube. So to prepare 250 milliliters of this solution, we will be using this volumetric flask that can measure very accurately all the way up to 250 milliliters. So now let's calculate the mass of the sodium carbonate. We need to prepare a 0.1 moles per decimeters cube concentrated sodium carbonate solution. Now the molar mass of sodium carbonate, anhydrous sodium carbonate, is going to be 106 grams per mole, and we are about to prepare 0.1 moles per decimeters cube concentrated solution. So if you are going to prepare 1 decimeters cube of this 0.1 moles per decimeters cube concentrated sodium carbonate solution, you would need 0.1 moles of sodium carbonate dissolved in 1 decimeters cube of solution. However, we are not going to be preparing 1 decimeters cube of this solution. Instead, we are going to be preparing quarter of that, meaning we are going to be preparing 250 milliliters or 250 cubic centimeters of this solution. So for 1 decimeters cube, if you need 0.1 moles, for a quarter of that volume, you would require 0.025 moles. And we know the number of moles we need, and we know the molar mass of the substance. So therefore, we can calculate the mass of sodium carbonate needed to prepare 0.1 moles per decimeters cube concentrated solution if you are going to prepare 250 milliliters of this solution. So since you know the number of moles we need and the molar mass, if you multiply 0.025 with 106 grams per mole, you are going to obtain a value of 2.65 grams, which is going to be the mass we need to measure to prepare this solution. So in order to do that, students, we have our triple beam balance we used a little while ago. So on this triple beam balance, we measured the mass of our watch glass. Now watch glass had a mass of 38.7. So you can see it still present here, 38.7. You can see on the top beam over here, the slider is at the 30th notch, meaning this reads 30 grams, and the bottom slider is at 8.7, indicating that the total of, or indicating the reading of this particular triple beam balance as it stands now is 38.7. So that is the mass that this particular triple beam reads right now, because the mass of this watch glass we have over here is 38.7. We confirmed it using a digital balance as well. So now we need to measure 2.65 grams of sodium carbonate. In order to measure this, we need to first add 2.65 to 38.7. So when you add 2.65 and 38.7, it happens to be, when you calculate it, it will get to the value 41.35. 41.35. So we need to first adjust these sliders so that this triple beam balance reads 41.35. After adjusting it in that manner, we will start to add sodium carbonate to our watch glass here until these two lines that we see here in the triple beam balance, the line that is on the arm of this triple beam balance and the base of this triple beam balance, until they align perfectly, we will add sodium carbonate to our watch glass here. So students, let's get the reading that we have over here in the triple beam balance up to 41.35. So are we going to move this middle slider? If you move it one notch to the left, it will read 100. Do we need to measure 100 of anything here? No, we need to measure 41.35. So we need to get these values to 41.35. So easiest way to get to 40 would be to move this top slider over to 40. Now when you move it to the correct location, you can hear that it falls into the correct notch, and you can see that it is at 40 now. And then we want this bottom beam, the slider at the bottom beam, to read 1.35. So if you bring it over here, it is now at 1, and then if you move it a little bit further, it becomes 1.3, and right between 1.3 and 1.4 would be 1.35. Now students, we have adjusted the reading of this triple beam balance to 41.35. 41.35. So now it is up to us to add sodium carbonate until the line that you see over here. Now it is not aligned, right? You can see it is now below this line that we have on the triple beam balance. The arm of the triple beam balance is now pointing further down, so therefore the two lines are not aligned with one another. As we add more and more anhydrous sodium carbonate onto the watch glass, you can see the triple beam balance is gradually, or the arm of the triple beam balance will gradually come up, and you will see that they will start to align once more. We will continue to add sodium carbonate, anhydrous sodium carbonate, until we see that these two lines align with one another. You can see at this point, you can see it has moved up a little bit. The arm of the triple beam balance is now gradually aligning with our two lines. The arm of the triple beam balance is gradually aligning with the line on the base. So we have to add a little bit more. Now at this point, students, we can see it has aligned with the line in the base. So the two lines are now aligning perfectly, meaning it is now balanced, indicating the mass that we have measured over here is having a total mass of 41.35. And we know out of this 41.35 total mass, 38.7 grams comes from the watch glass. The remainder, which is 2.65 grams, came from our sodium carbonate sample we added to this watch glass here. Now students, since we have measured our sodium carbonate sample accurately, not just any sodium carbonate, anhydrous sodium carbonate sample accurately, we can now move on to transferring this solid sample onto a volumetric flask to prepare our standard solution. So let's go ahead and do that. So let's move this out of the way for a while. Now we have our 250 milliliter volumetric flask, and you can see that there is a calibration mark over here. The calibration mark over here is etched onto the neck of our volumetric flask, and we have already learned when handling volumetric equipment you have to be very careful, because these equipment are properly calibrated at a specific temperature. In this case, this particular volumetric flask was calibrated at 20 degrees Celsius. So students, when you are handling them, be careful, don't keep it in the vicinity where you will be having a lot of movement, because you can easily knock them off. And when you are handling them, don't touch them from the neck over here and then start to swirl solutions around like so. Don't do that. And make sure the volumetric flask that you get is properly washed and dried. So students, we now need to transfer this solid sample into this volumetric flask. In order to do that, we will be using a funnel and a wash bottle. This wash bottle contains distilled water. So first we will be placing our funnel on the volumetric flask like so. But if you start transferring liquids while the volumetric flask and the funnel is placed like this, the only opening that you create is the opening that is found in the middle of the funnel. So as water or whatever the liquid goes in, the air that is replaced in the volumetric flask should come out from the same opening. So when that happens, you might see a small amount of water splashing around, because as water enters this volumetric flask, there will be a certain amount of air that is trying to escape the volumetric flask as water is replacing the air in the volumetric flask. And this region is completely sealed by the funnel, so therefore only this opening will allow the air to escape. So it is not ideal to just place it like this and then start pouring in your water to this. So whenever possible, lift it up a little bit and then start pouring in water, or in this case we are transferring the solid with the use of a wash bottle. So when you're doing that, lift up the funnel a little bit so that there will be enough space for the air to escape from the volumetric flask. Now, let's take our solid sample, and we have to place the solid sample like so, and we can lift it up. You can see now I can move the funnel along with the solid sample here, and then with the use of a wash bottle, you can wash down this solid onto our volumetric flask. You can see you can gradually wash it down onto our volumetric flask like so. You have to make sure the entire surface of the washed glass is completely washed. Afterwards, you can turn the washed glass around and wash the back of the watch glass a little as well, to ensure all of the sodium carbonate solid is transferred into our volumetric flask. Afterwards, you can wash the inside of the funnel and the tip of the funnel as well. After that, students, we can move on to observing what is present in our volumetric flask here. After keeping the funnel and the watch glass aside, we can now observe what is present in our volumetric flask. We can see there is some solid still undissolved in the volumetric flask. So the first thing you can do is to mix it really well. So when you're mixing, don't hold the volumetric flask from the top like so. So this neck area of the volumetric flask could break if you apply enough force. So therefore, do not swirl the volumetric flask around by holding it from the top of the volumetric flask. You have to hold the volumetric flask from the base of the neck of the volumetric flask like so. And then you can mix the contents in the volumetric flask by swirling the solution around until all of the solid dissolves. Now we can see almost all of the solid is dissolved. We can add a little bit more distilled water with the use of a funnel. And you can continue to mix it until all of the solid is completely dissolved. Now we can see that all of the solid is completely dissolved. There is no solid particles inside this volumetric flask. You don't see any solid particles inside this volumetric flask. So now we can proceed to add water all the way up to this calibration mark. When you're adding water, students, be careful if you're adding water with the help of a beaker. If you maintain a specific rate of addition of water, you will notice that this area where there's a larger, wider base, filling water would take some time, but as you pour water in the same constant speed, the remainder of the area will get filled very quickly. Especially once you reach the neck area, this neck area will get filled very, very fast. So therefore, you need to control the addition of water based on where the water level is. So after you get to this area, you can add water very slowly all the way up to the calibration mark. But afterwards, you can start adding water with the help of a dropper. we have a dropper here. We'll be using this dropper to add water close to the calibration mark. So let's use a funnel and we can proceed to add water gradually with the use of this funnel. You can see we can gradually add water onto our volumetric flask. Always use distilled water. Now I'm controlling the amount of water that I add. As you can see, we are at the neck area of the volumetric flask. From this point onwards, students, you can use a dropper to add the right amount of water until the bottom of the meniscus aligns perfectly well with the calibration mark that we have over here. So you can lift the volumetric flask up to your eye level. We will add water drop by drop until the last few drops. When you're adding the last few drops, to make sure that you very accurately add the last few drops to make sure the bottom of the meniscus aligns perfectly well with the calibration mark, we can place the volumetric flask on a table that is leveled, and then we can bring our eye level down to the level of the calibration mark, and then we can proceed to add the last few drops of water until the bottom of the meniscus aligns perfectly with the calibration mark. So if you observe now, the bottom of the meniscus and the calibration mark is perfectly aligned. This indicates that you have added the right amount of water to produce this 250 milliliter solution. If you by a mistake overshoot, meaning if you add a little bit more water than the required amount of water, let's say just a single drop or maybe 2 drops, when you're rushing, if you add a little bit extra water, you cannot simply remove it with the use of a dropper and say that you have produced a standard solution. If you add a few drops, or if you add extra few drops of water onto this solution, then you would have diluted the solution by the amount of water that you have added extra, or additional number of drops that you have added might have diluted the solution. And if you remove those 2 drops of water that you have added additionally, you will be removing certain amount of sodium carbonate along with those drops. At that point, we cannot be sure about the number of sodium carbonate moles that are present in this solution. So therefore, we cannot be sure about the concentration of this solution. The concentration of the solution might not be very accurately 0.1 moles per decimeter cube. It might be ever so slightly different to that. So at that point, it is not a standard solution. So you will have to restart this entire process again. So that is why we take a really good care when you're adding the last few drops, because we do not want to add even a single drop additionally making the meniscus appear slightly above the calibration mark. The meniscus and the calibration mark should perfectly align with one another. If the meniscus is slightly above the calibration mark, at that point you will have to restart this entire process from the point where we measure the sodium carbonate all the way up to addition of water. You will have to restart this process and do it one more time. So students, take precaution when you're adding the last few drops of water to produce this standard solution. After adding the last few drops, just to double check, you can bring it up to your eye level again and observe whether the meniscus is aligned with the calibration mark. And after preparing it, or after adding the right amount of water, we are still not done yet. You will have to mix this solution. To mix the solution well, you will place the stopper of our volumetric flask like so, and then we will apply some pressure and we'll close it with our finger like this, and then we will turn it upside down. We can turn it upside down a couple of times to make sure that this solution is well mixed to produce a homogeneous solution. Now we have prepared a standard solution where the concentration of sodium carbonate is 0.1 moles per decimeters cube. We know that this concentration is accurate as we measured the sodium carbonate needed to produce this concentration very accurately, and we made sure to transfer all of the solid without any spilling onto our volumetric flask. And finally, we made sure the amount of water added was added correctly until the bottom of the meniscus of this solution aligns perfectly with the calibration mark found in our volumetric flask. Now students, this is how we prepare a standard solution. Whenever you want to prepare a solution with a known concentration, you will have to follow these steps and you will have to use this equipment to produce a solution of known concentration or solution with accurately known concentration. Let's move on to the next session where we will be discussing additional theory parts and questions revolving around this experiment.